Hi there. So in the previous videos, we have sort of derived the Cauchy-Riemann conditions using two different ways of arriving at the Cauchy-Riemann equations. Let's do a couple of examples of how to use the Cauchy-Riemann equations to determine whether a given complex function is analytic or not. So just as a reminder and as a quick way to remember what the Cauchy-Riemann equations are, it's often useful to go back to the matrix representation and actually think about the Jacobian, and then see the constraints arising from the Jacobian when we think of the Jacobian as representing a complex number or a complex function. So in other words, recall that the Jacobian is for a transformation is of the form du dx, du dy, dv dx, and dv dy. And now if you recall the previous video where we talked about the matrix representation of a complex number, then the matrix representation is of the form A minus B and B, which represents the complex number A plus IB. And so if we sort of if we impose the condition that the Jacobian should represent some kind of a complex function, then we know that a constraint arises, and this gives us the Cauchy-Riemann conditions, which are that the diagonal entries should be equal. So du dx is equal to dv dy, and the off diagonal entries are negatives of each other. So dv dx is minus du dy. So this is a quick way to sort of keep deriving it and remember the Cauchy-Riemann conditions. So let me just write it down here, and the Cauchy-Riemann conditions, and then work out a few examples. That du dx is dv dy, and dv dx is minus du dy. Now we've also already seen, like, geometrically that let's consider two mappings to begin with, wz equals z, and we've already seen geometrically that this mapping is conformal because it preserves the angles between infinitesimal vectors emanating from a point. But let's try and use the Cauchy-Riemann conditions to find out whether it's analytic, which it should be, and also what is its derivative. So if we find out what u and v are, then u plus iv should be equal to x plus iy. Therefore, u is x and v is y. And now let's check the Cauchy-Riemann conditions. So the first one requires that du dx. The first one requires that du dx should be equal to dv dy. Now for this mapping, du dx, the partial derivative of u with respect to x, is 1, and dv dy is also 1, and therefore this condition is satisfied, right? We should also check the second condition. Both these conditions should be satisfied. So dv dx, now v does not have an x dependence, so for this particular function dv dx, the partial derivative of v with respect to x will be 0, and du dy, u also doesn't contain any dependence on y, so du dy is also 0, and therefore dv dx is actually equal to du dy or minus du dy. And so both these Cauchy-Riemann conditions are satisfied for this particular function, and so it is analytic. So this function is analytic. Now what is its derivative? So if you recall, the derivative of the function w prime z is of the form a plus ib, the complex number, and a we know is du dx plus I times b will be dv dx. Now du dx is 1, so this is 1, plus I dv dx is 0, so it's just 1. So dw dz or w prime z is actually just 1. And this is exactly what we will expect from a function of the form wz equals z if we differentiate it with respect to z. dw dz will be 1, in the sense that this is a very natural generalization of functions of a real variable, where let's say you have a function f of x equals x, then its derivative f prime x with respect to x is just 1, and that's exactly what's happening here. So this is one of the this is one function that we have sort of checked explicitly that it is analytic, and we have explicitly derived what its derivative is. Now let's check the other function we've also already seen geometrically, which is not analytic, which is the function wz equals z bar, and see why it's not analytic now. So in this case, u plus iv will be x minus iy, and therefore u is x and v is minus of y. Now the first Cauchy-Riemann condition requires, this is example 2, that du dx, we should check whether du dx is actually equal to dv dy. Now for this function, du dx is 1, whereas dv dy, the partial derivative of v with respect to y, is minus of 1. And therefore we see that du dx is not equal to dv dy. So the very first Cauchy-Riemann condition is not satisfied, it's violated, and therefore this function is not analytic. And in this case, it doesn't make sense to define a derivative of this function, because the function is not at all analytic, and so we cannot even talk about what is w prime z. It's not well defined, so w prime z does not exist. And this is exactly what we saw geometrically, because for the function wz equals z bar, the angles between infinitesimal vectors emanating from a point, although they are preserved in magnitude, their sense is reversed. And so this mapping is not conformal. It doesn't preserve both the magnitude and sense of the angle, and therefore it's also not analytic. And in this case, we have checked the same thing using the Cauchy-Riemann conditions, and found that the Cauchy-Riemann conditions are not, equations are not explicitly satisfied. And therefore the function is not analytic. So in the future videos, let's take up a few more examples, and in fact we'll see that the derivatives of many of the complex functions where it exists are sort of natural generalizations of the derivative of functions of one real variable, their counterparts their counterpart functions of one real variable, which is good because we don't have to sort of remember, there's no new sort of formulas that we need to remember, but it'll be good to explicitly check some of these functions. So let's take up a couple of more examples in future videos. See you there. Thanks.